just a moment. But it's going to be a twofold process. The first thing I'd like to do is look across the matrices that you got and see what they all have in common, for starters. And then secondly, to think about the more generalized question, right? Of these matrices, which ones of them were invertible? And what do you think is going to be the case in general when A transpose A is invertible? So let's start by going back to the matrices that you submitted. Here they are. So first of all, looking at the 2x2s that we have over in this box on the right-hand side of the screen, each of the teams has one. And first of all, somebody tell me in the chat channel something that all five of the matrices, I guess there's only four, but all five teams, 2x2 matrices, had in common. What do all the 2x2 have in common? Okay, so Jamie says that one of the things that they all have in common is that they have a non-zero determinant. That's something for 2x2s you can definitely check pretty easily. So I agree with that. All these will have a non-zero determinant. Brian also says that there's a surprising number of 9s and 17s showing up in these matrices. And I agree, right? Here's a 9, here's a 17. In this matrix, 9 and 17 appear over here in a fraction. This matrix here has a bunch of 17s. The matrix from team 3 has a 9 in it. So that's an interesting, potentially number theoretic connection here. Maybe I'll kind of ask in the margin, what do the numbers 9 and 17 have to do with this problem? What do they mean? I don't actually know the answer to that. Group 4, thank you, Brian, submits that they are all symmetric matrices. Now remember what symmetric means for a matrix. It means that if we reflect the entries of that matrix across its main diagonal, so for example, if I look at this matrix here, the matrix that team 4 and 5 contributed, its main diagonal goes down the entries 9 and 34. But then on either side of the diagonal, the entries are the same, negative 17, negative 17. So this matrix is a symmetric matrix. Whatever this matrix M is, if we take its transpose, it's equal to M itself. So symmetric is a property that all these matrices will enjoy. And you can see the short proof of why that will always be the case in our video number 3 from this past week. Team 1 has also contributed that all of these matrices had inverses. All of the 2x2 matrices that you discovered in this exercise were in fact invertible, which is really, really good news when it comes time to actually make a projection matrix out of this A, right? Because the projection matrix is defined by this matrix product, A times A transpose A inverse times A transpose. And in order to even use this formula, we need to know that A transpose A is invertible, because this inverse here has to exist in order to use this formula in the first place. And so you found that all of the 2x2 examples enjoyed that property of invertibility. By the way, team 1 and team 3 have really said the same thing according to linear algebra, right? Invertibility in linear algebra is equivalent for a square matrix to having a determinant which is not 0. Perhaps the best use of a determinant in all of linear algebra is to tell when a matrix is invertible. And having a non-zero determinant indicates that a matrix is in fact invertible. Okay, great. So that's what all these matrices have in common. What about the 3x3s? So give me 1 or 2 things that they have in common. We have only a couple up here on the screen, but compare those two with the ones that you got in your groups as well, and see if you can extract some meaning out of that into the chat channel. What do the 3x3s have in common with one another? All right, so one Brian is echoing another. Brian Sheehan says that all of these 3x3 matrix examples are symmetric as well. You can check that again, just looking at the main diagonal. This is Team 3's matrix. The main diagonal is there. And on either side of the main diagonal, the entries are the same. So these matrices also are equal to their own transposes. So these are all symmetric. Brian Witzkel also says all of these 3x3s have their determinant actually equal to 0 this time, which that makes a difference between the 3x3 example that we see here and the 2x2 example that we just did. So symmetry seems to be common to both the 2x2 and the 3x3 examples, but having a determinant of 0 is something that's different that happens in the 3x3 case. So what does that mean? What does determinant equals 0 mean for these 3x3 matrices? Very good. So having a determinant which is equal to 0 means that these 3x3 examples are not invertible. And it's probably good for a 3x3 or larger matrix to check to see whether its determinant is 0 first before you go about the awful business of actually trying to find its inverse. Because finding an inverse for a 3x3 or anything larger is pretty nasty to do by hand. It's not even a very tractable problem computationally. That's going to be one of our themes next week. Asking a computer to invert a large matrix is something that computers even don't do very efficiently. So clearly something here has changed between the 2x2 example and the 3x3 example. All of your 2x2 A transposés were invertible. Your 3x3 A transposés were not invertible. So coming back to this this set of questions. When was A transpose A invertible? In this example, I think you would agree that in the 2x2 cases. So it was invertible when we chose 2 vectors. For A, but not 3. So let me ask this question then in the channel. What is special in this example about choosing 2 vectors to build A instead of choosing 3? Why should we expect that choosing 2 vectors for the sake of the projection you're doing in this problem is a very different thing than trying to choose 3 vectors to compute the projection matrix in this problem that would make the 2-vector example work, give us an invertible A transpose A, but the 3-vector example not work? What do you think? What's the fundamental difference between those two things? Okay, so one observation coming from Jamie and from Team 3 is that even when A transpose A was 3 by 3, its rank was still 2. That's interesting. All right, so there is an important observation. Oh, and now Brian and Casey, so teams 4 and 1, have both come in with the same observation at the same time. Specifically, that in choosing 3 vectors from our list, we made a matrix whose columns are not linearly independent. Not linearly independent. And these two comments go together. So Jamie's observation that the rank of A is still 2, even when A is the 3 by 3. So in fact, even though I wrote A transpose A up here, we could actually just write A. Even when A had 3 columns in it, its rank was still 2. And the reason its rank is 2 is that there are only, in fact, 2 of the columns that are linearly independent from one another. Not all 3. Linearly independent. And what's the reason for that? The reason for that is that the columns that you were selecting, so all of the columns here, W, X, Y, and Z, that came from the vectors that I provided for you in this example, all of those columns came from the same two-dimensional subspace. Namely, they all came from S itself. So W, X, Y, and Z were all vectors lying in the same plane. This is a rough sketch. I'm not trying to be accurate with it. But W, X, Y, and Z all belong to the same plane. And therefore, if I choose 2 of them, let's say I chose W and Z or something like that, and I make a matrix out of them as columns, this matrix is going to have a rank of 2 because the set of vectors W and Z is linearly independent. But if I choose 3 of them, let's say W, Y, and Z, the rank of that matrix is still going to be 2. Because even though there are 3 vectors, only 2 of them, at most, are linearly independent one from another. And you can check that for the examples that you were provided, in fact, any pair of them will give you a linearly independent set. But because collectively they all lie in the same two-dimensional plane, the two-dimensional subspace, at most 2 of them may be linearly independent. And so the rank of A is 2, regardless of how many vectors we stuff into the columns to make it. And therefore, we could extend this to say A transpose A is invertible exactly when the columns of A are linearly independent. And remember, we were hoping that this would be a criterion that we can control. Because in a projection problem, we want to have an invertible matrix A transpose A so that we can actually build the projection matrix P. And this is the really good news, is that in a projection problem, what we're doing is we're starting with a subspace. We're starting here. We know what the subspace is. In this example, the subspace was the set of all points in R3, such that 3x plus 2y plus 2z is equal to 0. And then from that subspace, we had to determine, and this was the step that I did for you when I wrote these problems, but in general, you would have to determine, pick vectors in this subspace, vectors in S, to form the columns of A. And it's because of this choice, because of our own ability to pick which vectors we use here, that we can guarantee that we can pick one for which A is, in fact, linearly independent. So that's the good news. As long as the columns of the matrix are linearly independent, then A transpose A will be invertible, and so therefore the projection matrix formula will actually give us a matrix. Before we go any further with this, let me ask in the chat channel here for any questions.